Okay, hello everyone for this Sfen Index seminar on digital application for nuclear industry. So today we'll talk about case studies on operation maintenance. It's my pleasure to moderate with Sebastien this meeting. So just a few words about me, and I will let the floor to Sebastien. So my name is Patrick Morilhat. I'm working as a program manager for nuclear performance at EDF, the French public utility in electricity. Sebastien, present yourself.
Thank you, Patrick. Very pleased to share this session with you. I'm Sebastien Diaz. I'm working for NUVIA company, which is a specialist company in the nuclear industry, and I've been working for 20 years in the nuclear industry. My background is civil engineering.
Okay, so we'll just jump into the presentation. So I will let Sebastien present the first presentation by CEA.
Thank you, Patrick. So first, I wish to introduce Reynald Boillot from CEA, the French Atomic Energy Research Center. He will explain a project related to the use of several digitalization techniques to train and develop skills on reactor technologies and operations through the project name EVOC for Enhanced Virtual Open Core. So Reynald started his career 17 years ago in the French Navy as a mechanician and a nuclear supervisor. Then he moved to Areva as senior trainer. Then he gradually evolved within the group to train the expert in operation of nuclear facility and reactor training center manager. And then he switched from Areva to Orano as innovation direction as open innovation manager, working on several new technology like intelligent sensors, robotics. And then he decided to join ENSTN in the CEA of Saclay as training project manager. So please, Reynald, the floor is yours.
Thank you very much. Hello, everybody. I share my presentation. You can see my screen?
Yeah. Yes.
Yeah, okay. Thank you very much. So my name is Reynald Boillot. I am from the French School of Low Carbon Energy and Health Technology, INSTL. So I'm involved as a training project manager on nuclear power plant cross-cutting team leader. I'm here to present you the new platform EVOC Nuclear Experience. So for Genesis, for decades, INSTN had been using CEA's research reactors such as Egis reactor to train its students and professionals from all across the nuclear industry in France and abroad. While the necessity to train more students and professionals on reactor technologies was coming critical and growing a few years before, and despite this reactor shutdown in 2018, it was essential for INSTN to maintain the higher level of its education quality and improve the skills and knowledge transfer efficiency. So thanks to the emergence of new digital capabilities, INSTN and CEA decided to accompany this shutdown with knowledge management action plans. Moreover, INSTN took the opportunity to expand the training proposal with covering previously inaccessible operating domains. The idea was to develop a global project beneficial to CEA on INSTN and on the global nuclear community at large. So as you can see on the screen, here you have the picture of this reactor with an open pool reactor here. The first step of development of EVOC with the first training of EVOC platform in 2019. And now, 3 years after, we are with this kind of opportunity and platform. I will explain all the part here. We're glad to have now the Sfen Awards education and training this year. It's very important for us for visibility on the platform. So first, the first part of EVOC nuclear experience is control panel. The control panel is a replica of a material testing reactor control panel. It embeds a nuclear physics phenomena simulator developed by the CERMA of the CEA. The simulator currently replicates the behavior of the Egis training reactor and reacts to students' trainees' actions on the control panel and in the reactor hall. The aim of the control panel and its embedded simulator is to enhance the understanding of the neutron kinetics inside the core. All the curves are simulated on through to life. Students and operators in training can operate the reactor from shutdown to full power following the instruction given by our trainers. The trainers are experimented operators and supervisors coming from the old the research reactor of the CEA. The control panel has different alarms also displays to warn students and trainees of faulty operations. It enables learning by doing and learning by mistakes. EVOC nuclear experience includes also a mixed reality reactor hall for students and trainees to explore through virtual reality headsets and interact with each other with physical objects. Virtual reality is used to recreate the entire nuclear facility in which students can move freely and interact with the environment. The core is immersed in the pool and all effects on the power, such as the Cherenkov effect, are simulated. Guided by protective rails, students can visit the hall and localize the points of interest of the reactor. They can follow the evolution of the power of the pile and the movement of the control rods. Interactive commands for manual loading and unloading for fuel elements in the core are currently being developed. During group visits, students equipped with virtual helmets can interact through their avatars. So on the pictures, it's an old technology you can see here with backpacks. All the calculators are here on link with the helmet here. It's a technology from Vive, HTC Vive. People are here in an external view, as you can see here, with a backpack on the back. And during the simulation, there are through avatars, and they can interact with the different parts of the reactor. Here you can see a few pictures coming from the old reactor. Also, here you have all the old reactor here. The pool, because it's an open pool reactor, so it's a 7 meters depth pool. Here you can see one of the avatars to take into account. So important this part because to take into account the cognitive load of the trainees necessary for proprioception and embodiment through avatars, we have implemented female and male ones. So a battery of avatars, male and females. The first one you can see here what the male and the female is here. We have also implemented screens for better understanding of the different operations and phenomena. As you can see here, the reactor on the map to take different parts of the fuel. We have also a software solution to allow the interaction between participants on the mixed reality environment through any time, without any time distortions. So the name is Interact. It is also an interaction between, it also allows the interaction between the simulator embedded in the control panel and the mixed reality control reactor hall. These two technologies work together. An action carried out on the simulator has the repercussions in the virtual environment and vice versa. The part here is interesting to see it has been developed by the CEA. So the joysticks use a human-machine interface. So it's a Matisse technology proposed at CES Las Vegas in 2018, which emulates the sense of touch. It relies on smart field, magnetorheological fluid, This field that varies its apparent viscosity is able to generate very rich kinetic perceptions and then enhance the learner experience. So here we see here the changing room. As you can see, the control room is here with the simulator. And as projects for next year, here you have the whole of the reactor. As you can see in this picture, up here, you are in the whole reactor. And we are now in the project to develop a changing local rooms here. So this one is interesting because it's equipped with connected radiation supervision device wired up to an instructor tablet to put students and trainees in real nuclear power plant conditions. This control is made through technology of ultra-wideband technology. It allows for the transmission of a large amount of signal energy without interfering with conventional narrowband on carried wave transmission with the same frequency band. This simulation includes individual radiation detectors, because the card, for example, radiation sources also, radiation zone entry and exit terminals, as you can see in the picture here. Aerosol dose tracking detector with balise, called balise Edgar. Aerosol also, it's one, on alarms also. It's a real representation of what you can find in a real device, in a real facility. Sorry. So in this part, we use also an accidental situation because, as I said before, we can go through different simulation from shutdown to full power. But we have also implemented the simulation of an accidental situation. It's a nuclear experience of this kind of situation. So it's a criticality accident. The modelization is very realistic because all the data of this accident was taken from an actual accident on Egis reactor in 1968. You can find different data on the web. It's not open source now. So we have taken all the elements of the report and made the modelization of every part of the accident. So with the experience of our operators and trainers, we will try to have something very realistic during the accidents. So you have a picture here of the situation during the accidents with the steam, with everything like this. And we are also linked with the other facility of INSTN. Here you have the simulator of a terminal, exit terminal, to detect contaminated people. And then they are taken in charge in a control room just close to the simulation by the security services. So while the safety and security rules of a nuclear facility do not apply, the accuracy of the simulation and the virtual reality evoke nuclear experience, coupled with physical element, allow developing safety culture and behaviors, even during a crisis management. So with the new technologies, this one is very interesting. So autonomous virtual reality helmets, because it's now proven interesting to promote proprioception during immersion and limit the cognitive load associated with the wearing equipment. So evoke nuclear experience, the step forward capabilities for skill development in reactor physics for students and future operators. Cutting-edge digital solutions coupled with decades of accumulated experience in training and ambitious reactor present considerable benefits for trainer and trainees, like facilitated access of the facility compared to a real facility, less paperwork and background checks. The possibility to train several people at the same time on several groups of people at the same day, the groups of about now we try to have groups of about 10 or 12 people at the same time, involved in the control room, and 6 involved in the control room, and 6 in the hall of the reactor. So we can mix operating team, maintenance team, and radiation protection service. So that's quite interesting because you are not allowed to do that during the training process of each team. Operating team their own trainings, maintenance team their own trainings also, and they are not allowed to meet together before being in a real situation, in a real facility. And evoke nuclear experience is able to evaluate the different behaviors, evaluate the interfaces between those different teams. The relevance of accuracy of the simulation, as you can see, because of the simulation, all the data are coming from real situation, real reactor, and the behavior of the simulator is realistic, as we can find in the whole reactor. The whole of the reactor has been developed from the data coming from Egis reactor. So it's like really like it was before the shutdown of the reactor. The high impact training mixes the scientific training and the safety culture development through immersion in a real facility. But the high impact training also due to the trainee's involvement in his training process. So it's interesting to learn with this kind of tool. Embedded learning with the remote experience before a face-to-face training. So with the learning management system, we have developed a few modules of e-learning, can allow the people a good experience of evoke of the trainings before coming directly on the facility. I think perhaps I'm too quickly, but thank you for attention.
You are perfectly on time.
Yes,
so.
just on time. Great.
Okay.
Thank you, Reynald, for your presentation. Very interesting. We have a couple of questions, so I will try to rephrase. So there is a question about the autonomy of the evoke application related to the Vive power autonomy, especially. I need a lens, I can imagine.
Yes, bonjour Jean-Bernard. Like it is a small technology. Now this kind of technology allows an autonomy of about 30 minutes. That's enough for a normal operation because most of the operations in the virtual world just take 5 or 10 minutes at least. And the accidental situation is very quick. The kinetic is less than 1 second before the accident. So 30 minutes are enough to do all the operations, even loading the core, unloading the core, because we move only 4 fuel elements during this part. That's quite enough.
Okay, thanks. There is another question. Perhaps the two questions are linked, but do you manage any statistics for the learner, for the trainees? And how often a mistake is made? Do you have some statistics about that?
No, I don't have yet enough statistics to do that. Since 2019, we've trained only 600 people. So the only way you can see now it's that people involved during the simulation can make few mistakes of the understanding of the behavior of the core, and it's useful to have that feedback now, but to try to make statistics more and more statistics to evaluate the efficiency of the system.
Okay, I will just take two questions more because we are a little bit late. So there is a question about is this platform open to any company first, and how many trainees per year can attend such digital training?
So yes, this platform is open to any company at this time. It's involved in the Génie Atomique first, but also for master nuclear energy. In February, the CNAM will use this platform. So yes, it's completely open. We can turn at this time regarding the different programs of maintenance. We can the experience now it's more than 300 people per year, but we can improve that because at this time also those platform needed 2 years before needed lots of works, and now it's completely available, so we can do the job with more than 300 people per year.
Okay. Thank you. Thanks a lot, Reynald, for this very interesting presentation. And now, Patrick, I let you go further with robotics.
Yeah. So I have pleasure to introduce Mr. Songhae from KHNP, the Korean hydro and nuclear company. So Songhae has been conducting research on the application of various advanced technology in NPPs for many years now. Recently, he is in charge of developing automatic predictive diagnosis technology and use of artificial intelligence for the monitoring and the diagnosis of nuclear assets at KHNP. So just a reminder for Mr. Songhae, you have 15 minutes for your presentation. And a reminder for the attendees, you have a S as Slido top on your screen, and you click on this button if you want to raise some questions. So, Mr. Songhae, the floor is yours.
Okay, thank you. Hello, everyone. Thank you for being here today. Let me introduce myself. My name is Songhae. I am in charge of developing the automatic predictive diagnosis technology at KHNP. KHNP is a state-owned public corporation responsible for the operation of 30 nuclear power plants in the Republic of Korea. It is an honor to introduce KHNP AMD system in front of many foreign experts. So, excuse me. The order of presentation is as follows. Digital KHNP vision. As you can see, KHNP declared the digital KHNP vision as an energy 4.0 global leader, both internally and externally in 2020. Phase 1 is foundation establishment by 2022. We are digitizing our business process through various pilot projects to which first industrial technology are applied. Phase 2 is an expansion phase by 2025. A digital twin will be established by building a big data platform dedicated to KHNP. Phase 3 is a global leader. By the 2031, KHNP will secure its own customized smart platform. This is the KHNP technology trend of intelligent monitoring diagnosis field. From 2013 to 2016, we completed the environment of early warning technology for integrated monitoring of all nuclear power plants and operated the tower at the KHNP headquarters. From 2022, the AMD Center is operating separately. to monitor the status of major equipment in 26 operating nuclear power plants and perform automatic predictive diagnosis. Through this, KHNP intended to strengthen the safety, transparency, reliability for nuclear power plant operation. This is the development process of AIMD system. The business goal is to prevent accidental failure of a nuclear power plant due to equipment failure. In 2017, through the first phase of the project, we carried out a pilot project for the development of automatic predictive technology regarding 300 equipment of 5 types rotating equipment. In the second phase of the project, the number of major equipment in 26 nuclear power plants was expanded to 12,387 equipment, and technical advancement was carried out. Instruction background. Existing power plant equipment monitoring and diagnosis systems are scattered and operated, so making it difficult comparative diagnosis of similar equipment and prevent failures. In addition, in order to overcome the problem, rely on manual diagnosis and individual experts. Accordingly, the development of AIMD system was required. This is a conceptual diagram of the AIMD center. By integrating, monitoring, and diagnosis the major equipment of a power plant from a remote location, it becomes possible to implement a smart platform and to achieve zero equipment failure. In other words, by using the AIMD system at a remote location, abnormal sign of major equipment of power plants can be detected earlier and taken action. Unexpected shutdown of nuclear power plant can be prevented. The picture on the bottom right are actually implemented screen in the system. Applied technology. In the first phase, file development, network connection, big data optimizing, and AI algorithm development were performed. In the second stage, technology advancement was carried out through thermal imaging, deep learning, comparative diagnosis of similar equipment, and linking with the wireless sensor system. System building process. Network connection of a diagnosis system scattered in power plant, big data construction, measurement error program development to ensure reliability of measure data, rule-based diagnostic algorithm development, machine learning algorithm development, and 3D visualization model development were carried in this order. This is a network schematic diagram of the system. We built big data through unidirectional device and file copy of measured data of power plant equipment using the built big data and automatic diagnosis engine. The ThemeWorks platform informed the user about the diagnosis result. This system is developed in consideration of a web service, so it can be used by power plant equipment managers. Predictive diagnostic analysis algorithm. In the linked connection of equipment measured data, operation and engineering information of equipment are integrated. The diagnosis is performed using an AI-based analysis solution, and comparative diagnosis of similar equipment and comprehensive analysis are performed. The below picture are actual implemented system screen. AMD center operation. The KHNP AMD system has the brand name of Prometheus. After 2 years of pilot operation, official operation began last year. We have been conducting online condition monitoring and diagnostics analysis for major equipment in 26 operating nuclear power plants. Last page. This is the expected effect. We have secured the world's largest automatic predictive diagnosis model for 12,387 rotating electric equipment of 675 types. As a result, KHNP has been able to support optimal maintenance of major equipment of nuclear power plants, ease regulatory requirements, enhance reliability of nuclear power plant, and secure an advantage in export competitiveness. Thank you for your attention.
Okay, you can now we can have your video if you wish. Now you have time enough for that.
Yeah, wait a minute. I will show the promotional video about the technical development.
Okay. We don't have the sound, but we can read the subtitles. Thank you, Mr. Ye, for that. Thank you very much. We have a couple of questions in the chat for you. Yeah. Question about a question raised by cybersecurity aspects. The question about wireless acceptability in a power plant of this technology. So what do you think about that?
In this field of remote intelligent monitoring and diagnosis, the cybersecurity requirements were met by applying a one-way device for network connection of device. So no problem. Yeah.
Yeah, no problem. Okay. Another question is about is human expertise involved in the machine learning that you have developed, or it's fully automatic, or do you mix human expertise and machine learning, or what about that?
Yes. Machine learning is the most important thing is failure data. Big data is history. So we can a lot of operation history, machine history is saved database. So to secure the reliability of the acquired local data, measurement error detection program is installed in the AMD system. Yes, that's it. Yeah.
Okay. Okay. Thank you very much again for your presentation. And now, Sebastien, we move on to the next presentation.
Thank you, Patrick. So let's say to a diagnosis. So Mr. Romain Molinas from Vulcain Engineering and Martin Leloc from Quantmetry will present an interesting study case, which is an application of IA to address maintenance diagnosis. So Romain Molinas is transformation consultant for Vulcain Engineering. So he works in artificial intelligence research, specializing in digital transformation and enterprise architecture. He supports international industry leading companies in order to secure complex projects. Martin Leloc is director of Quantmetry commercial activities in the industry and energy sector. He has been working with major French companies for more than 12 years to support their data-driven transformation. So please, gentlemen, the floor is yours.
Thank you, Sebastien, for your introduction. So today we are pleased to introduce you an innovative approach throughout this embedded AI for automatic defect diagnosis use case. So basically, this presentation will change from the regular use case that about AI that ingest large amount of data through high-powered computers. This approach indeed is perfectly integrated in a maintenance context by relying on the know-how of experts combined with operational data that are heterogeneous as well as sometimes of very low quality and that needed to be run into some dedicated devices that are used on site for maintenance activities. So speaking about maintenance activities, at Vulcain, we have built a strong expertise on the different maintenance activities, had throughout some problems that we wanted to solve with our clients, a lot of unit shutdown issues, obsolescence management, as well as asset management in France, but also in an international context in Belgium, UK. And we wanted to be sure to secure all the production commitments, as well as improve the performance by optimizing the production cost. So when it comes to maintenance and operation, our experts have raised unanimously difficulties, especially in managing how the know-how over time and years is managed, and how all the maintenance information are capitalized, especially throughout all of the years of different maintenance program, etc., and how difficult it could be to be reused in order to achieve a dedicated consensus for a specific diagnosis. So I would let you, Martin, present this approach that has been successfully implemented in a natural gas transportation context. And then after that, we will look at all the perspective of application in the nuclear maintenance field.
Thanks a lot, Romain. So welcome everybody. So as explained, we will today share a use case presentation that an experimentation we delivered with GRT Gas, which is a French leader on gas transportation. And we developed this solution with them in order to improve the maintenance diagnosis based on AI and especially on computer vision, with computer vision. We developed this prototype, this experimentation, with 3 entities of GRT Gas. Especially the RICE entities, which is the research department oriented on renewable gas and innovation for the business. First of all, let's explain the context. So each year, GRT Gas send thousands of operators to control, to verify, and to proceed to maintenance operations all along the pipelines. And so that's something really difficult to achieve in terms of training, in terms of safety, and in terms of efficiency. So here, the main pain point that we want to tackle with this AI-based solution is the subjectivity of the diagnosis, because we detect, or the business detect, that there is a wide difference of diagnosis for the same pipeline defects between each operators. So some of them could ask for a repair, or some of them can ask just for a repaint. So that's an example we will see at the end of this presentation, that we are now expanding the field of application of this solution, but that leads to some additional costs, some diversity in the maintenance that we want to avoid with this solution. So the question was how to provide to each operators a solution, a mobile solution to help them to diagnose. It's a bit like having an expert to help you to take the right decision when you are on the field. And so it will help to as I said, to remove the subjectivity of the diagnosis, but also it will help to capitalize on expert knowledge and to have a common truth for maintenance operation. So how, before explaining how we train this model, I will just highlight the 2 main constraints we faced during this project. The first one was the size of the data sets, because as Romain said, we always talk about AI and big data with a lot of data sets, a lot of data points, but here we only have the chance to capture roughly 400 images of defects. And so this low number of images was a huge constraint for the AI model training. The second constraint was how to embed an AI in a common mobile, because as you know, training and inferring with the AI model could cost a lot of computing power that you don't have on your smartphone. If you are using the solution and that all your battery is leaking because it's too heavy in terms of consumption, the solution is just not able to work. I see we have a question about the sharing. Is everybody seeing the slides?
Yes, it seems. Martin, please, we have to move forward. So please, can you try to speed up if we want to have some time to raise some question? Okay.
Sure.
Thank you.
Let's continue. So basically, to train a model, you will first, as I said, collect the data set in real condition. And it's important to be in real condition, because if it's synthetic data, you will not be able to have a good performance, a good accuracy of your model. So the second part, and that's the one I will focus on, is how we include experts' knowledge in the AI, because it's not magic and it's not just training the model on the images, but it's taking some experts, ask them to labelize the data, ask them if they will repair it or if they will repaint it, and we ask this for a bunch of experts to get, in fact, the knowledge of those people into the AI model and to use this to train the model. And so last is we use transfer learning to do so. Why transfer learning? Because as I said, we only have 400 of images. Is not enough to train a computer vision AI model. But with transfer learning, you use a pre-trained model and you add the expertise, the specialization of the model at the end of this. And so with all of this, we get globally an accuracy over 80%, 85% to be compliant with the expert recommendation for this diagnosis. Once we did that, we only have the first part of the model, because we have a model that is able to run on servers, on big data platforms, not on smartphones. And so that's why after that, we apply another steps, which is the model optimization for mobile. And here we use mainly two things. First, optimized libraries for mobile computers. So that's the first step. And then we use models pruning. What it is, you know that in a neural network, you have a lot of links between each node to understand an image. So here we cut the ones we have the less decision power in order to transform the model to a lighter version of this AI. At the end, by doing this, insert expert knowledge and prune model and use optimized libraries, we achieve to get a similar accuracy versus the first deep learning architecture we use. And we have a model that is able to run on a mobile device with 4 times less RAM and 5 times faster inference response.
Okay, thank you, Martin, for this presentation. You have finished? No?
No, we will continue.
Yes, we have I would say 2 to 3 minutes more, if it's possible, in order to explain more the perspective is possible quickly.
Okay, 2 minutes, then no question.
Okay,
so
okay, perfect. I'll let you finish, Martin.
No, it's okay. Okay. Go to the
so if we are talking about perspective in terms of AI application and maintenance, we have today a wide range of enablers that exist to ease the application in nuclear industry, which is sometimes a bit resilient in terms of change. So it includes, of course, algorithm capabilities, dedicated to topics, to be easily applied on various data structures on different type of devices, we just saw. We have also technology accessibilities in order to drastically drop the cost and to easily be integrated within an existing information system, and also Trust AI, which helped the explainability of the models, how it could, and also its robustness, as well as how does the model fits and is aligned with the value of the companies. So the idea is to implement an approach that is built hand in hand between on-site experts and some data science teams. And the added value lies in the ability to optimize the combination of the expertise, know-how, and the associated decision-making with a limited operational data set that is currently available on site. And the objective is to simulate this consensus that Martin explained to you of experts on a well-defined technical control task under a very constrained environment. And if we talk about an example that we are working on currently is how to optimize the visual control and conformity analysis of some anchoring system in an operational set. So the objective will be to optimize in a very time-consuming control of the systems by integrating some precise deviation criteria to secure out the whole process and the respect of the conformity criteria. And the idea is to use all the knowledge from the conformity teams, as well as some information provided into some reports, some pictures, even if it's some low quality, in order to provide a tool that is capable of identifying all of this conformity and non-conformity of the anchoring system. And when we are talking about 5,000, 6,000 of equipment, I think that we can see the added value. And more importantly, it will be the end of this presentation, is that the optimization of the maintenance program is not only to be considered at the level of a unit, but also to be easily benefited by the whole nuclear plant and the whole nuclear plant series that has some maintenance program, because there is a lot of identical maintenance activities as well as identical equipments. And this could be made possible by sharing the knowledge that is capitalized and encapsulated by this type of technologies with all of these inspection teams, and to provide it into this kind of tool. And moreover, this value can be enriched also with application on other sites, with the integration of a new expert point of view, as well as maybe new data that are available on different sites. And it could be desirable to be able to benefit from this optimization of some maintenance program by using this replicability of the plants in operation, as we all know that the ISN can do the same when identifying a problem on your unit and impact all the different identical units when there is a problem. So maybe it could be a benefit for maintenance activities. Thank you for your attention.
Thank you, gentlemen. We just asked one question from Jean-Bernard. What could be your recommendation for existing fine-tuned process for which only few images reveals defaults, like 2 or 3% of the database? Do you have any requirements?
Yes, that's a common challenge we face, because failures are by default non-nominal things, So to improve this and to tackle this, we need to make some data augmentation in order to balance the data set. So you need to have a higher proportion of defaults. And to do so, you have different solutions. One of them is to use generative design to generate some images with those defaults. You also could use style transfer to create, in fact, a part of your data set which gets some realistic defaults. So that's the main things, is to switch to this 2% to maybe something like 15 or 20% to help the model to train.
Okay, clear. Thank you, gentlemen. Patrick?
Yes. Now, so we have had this presentation on one presentation on training, two others on diagnosis, and now we are moving on to robotics with Mr. Pilon from Atkins. So Christophe spent a decade working for on robotics for factory automation and other industry, and he is presently leading the robotics team for nuclear sector at Atkins. So, Martin, Christophe, sorry, you have the floor.
Thank you very much, Patrick. Hello, everybody. Yes, so you should see my screen now. And
yes.
Oh, just 1 second. Okay. So yes, hi, everybody. So today we'll talk about how we use robots on nuclear sites. But before we dive into the details, I just want to spend a minute on robotics and automation outside our industry for some context. So if you're familiar with robotics, you have probably heard of the 3Ds of robotics. So if a task is dirty, dull, or dangerous, a robot should be doing it. Okay, so that's the base principle we try to follow. And generally speaking, we have two large categories of robots. On the left, we have industrial robots, so normally used in a factory automation setting. Think of automotive, electronics, packaging, for example. So in this industry, we have typically high volume and low mix type of processes, which are ideal for robotics because robots are great at simple, repetitive tasks. So spot welding, for example, is a good example in a car factory, or palletizing in a packaging factory. So I've been in the nuclear industry for about 1 year now. My background is in the industrial robotics, and this is what I'm trying to bring and to make use of mostly in the nuclear industry now. But what we can see now on the right is the service robot space with industries like agriculture, restaurants, logistics. And in these areas, we have challenges based on unstructured environment, high mix processes, and we need robots to be smarter in these industries because they need to adapt to environments used or designed for human. So some of the enablers for these industries are AI, machine learning, machine vision, collaborative robots, so robots that are designed, that are intended to be used in closer proximity to people. And in general, we have a context of lower hardware cost, higher labor cost, labor shortages. So all of these factors contribute to the emergence of robots in new industries. So the highlight here on this slide is robots are not limited to factory automation anymore. So what does it mean for the nuclear industry? I think the purpose is the same. We have plenty of dirty, dull, and dangerous tasks. In terms of challenges, of course, hazardous environments are also challenging for robots, and the robots also need to work in existing legacy sites that are designed for manual work. However, if we look at the enablers, we can benefit from technologies that are being developed for other industries, like the service robot space, for example. And compared to other industries, I think the safety and the cost benefits should make it easier to justify business cases, to justify investment into automation. Then on the right, we have the types of applications that we are working on. I like to split them in these three categories. The first one is data collection for typically surveying and inspection applications, normally carried by mobile robots. We have remote operations or remote handling applications where we want to augment people with robots that are teleoperated. And then finally, we have what we call industrial operations, use cases where we can automate the process, typically using industrial robots. So let's look at a few examples. The first one is going to be about remote data collection. I'm sure many of you will have seen Spot by now. Spot is a walking robot that is made by Boston Dynamics, and we use it for remote surveys and inspections. I'll start playing the video. It might be a bit laggy, but hopefully you'll still follow. And Spot is a platform, so it's very interesting for the nuclear industry because of its mobility, of its agility. It can go up and down stairs. It can go over obstacles, can go around obstacles with the built-in navigation. And to make it useful on site, we equip it with different payloads. The most common examples would be cameras, thermal cameras, 3D scanners, LiDAR, or more specialized equipment like radiation mapping payloads, for example. We also have a robot arm for manipulation tasks. We can open doors, push buttons, turn valves, grasp objects, and you can either teleoperate the robot or you can send it on autonomous missions. So for routine surveys and inspection tasks, for example. So the main purpose is really to avoid sending people in hazardous environments. It's for safety. But by automating the data collection activities with the robot, you can also improve the quality and the consistency of your data. So if you think of a digital twin, I think it's been a popular topic in this conference and a popular topic in the nuclear industry these days. Well, if you have a robot feeding data into a digital twin, then you have a very good consistency of data. If you look at this other video, it's a different application where we're using Spot to perform a remote cleanup for different types of waste, like this bag of waste, for example. And in this case, Spot is still operated from a safe space outside a contaminated cell. And we keep Spot with different tools, different end-of-arm tooling to move waste around and to make sure that when people do have to get in a specific hazardous area, at least most of the cleanup is done, and we've done to the best of our ability, we've reduced the risk to people. So now moving on to Argo, which is the Atkins remote glove box operations. Here, the main objective is to reduce the risk to people and to reduce the risk of injury to glove box operators. So we've seen safety incidents in the past involving manipulating sharp objects inside the glove box. So this is what we are addressing here. And it's an example of a teleoperated system where we're not looking to fully automate an operation, but we do want to augment the operator with better tools to do the work safely. And our solution is to use a collaborative robot. So it's a Kinova Gen 3 arm. And this robot happens to fit through the existing standard ports of a glove box. And what we want to do is we want to teleoperate the robot to carry different tasks for glove box operation and decommissioning. So I'll play the video and show some of the tools that we've been developing. First of all, we have cameras, so either 2D or 3D cameras to show the operator what's inside the workspace. And we can also generate 3D point clouds with these sensors. And then we've tested different tools to make sure that the robot would be adapted, would be able to perform some of the common operations, like using this impact driver, for example, to remove bolts and nuts. We've removed nuts up to M20 in this case, so quite a high torque. Then we've looked at some different size reduction applications using a plasma cutter like this one. In this case, we have a pre-programmed path. It's not fully teleoperated, but it's partly autonomous, let's say, with pre-programmed routines. We've tested this angle grinder as well, again in a pre-programmed mode, to make sure that the torque applied to the robot was still under the limit. And then if I jump to the next tool here, this is another tool that we're developing. It's a robotic hand that is inspired by the human and a prosthetic hand. Because most of the tasks are currently done by people, designed for human hand, this gives us a lot of options to grasp different objects, to use different tools, and gives us overall a very good dexterity for the robot to manipulate objects within the glove box. So it's a great general purpose tool. And finally, if I play this one here, we're developing what we call a digital twin applied to the robot. So it's a virtual robot that is linked to the physical robot, and we use it as a user interface for to send commands to move the robot and to test commands that are sent to the actual robot and make sure everything is running as expected before we launch a command on a physical robot. Then moving on to the laser cutting modules. Here we are at the other end of the spectrum. So we are automating tasks with industrial robots. So these are 2 laser cutting systems that are currently deployed in the UK. And the objective is to reduce the volume, reduce the size of old fuel skips and alpha contaminated glove boxes. So at the top here, we have the skip size reduction project. We have one robot that is cutting panels with a laser cutting tool. And you'll see a second robot come in shortly and take scans of some of the areas on the skip to make sure that the geometry is corresponding to the theoretical positions, making changes if necessary. And then this second larger robot is also equipped with a magnetic gripper to hold the panels. So the sequence is, as you'll see a bit later in the video, that the first robot cuts the panel while it's being held by the larger robot, and then the larger robot picks and places the panels to a secondary container. And effectively, when we cut 2 of these skips, we can fill a third one of the same skips with the panels of 2 others. So we're effectively reducing the volume by 2/3 by doing this and solving a big problem on site. If I play the second video here, what you can see now is the offline programming tool that we're using to develop all the logic, all the robot paths offline. It's all pre-programmed and tested in a virtual cell before it runs on a physical system. In this case, we're also using a Fanuc industrial robots in a 2-axis positioning table. And this, what we're doing here was we're cutting a glove box in pieces that are fed out to another container. So I'm going to move and you'll see the physical system running. And here you see small parts being fed with a conveyor outside of the cell to a 200 liters drum. And in this sequence, there's also a human in the loop, just to build the confidence, just to make sure we monitor the system as it's running, and each step is acknowledged and authorized by a user currently. So the last project I want to talk about is the sort and segregate system. This is a system we're developing to reduce safety risk and to improve the productivity of the sort and seg operation. So because of the storage cost difference between intermediate level waste and low level waste, optimizing the sorting and the packaging of the waste can lead to very significant cost savings. So what we have here is also an industrial robot with a vision system that can automatically segment and identify waste items from a pile. Then a grasping algorithm is used to generate grasp options. The robot will then pick an individual waste item from a pile and move it to a monitoring zone where we measure the volume, the weight, we verify the material type and the dose rate of the item. And based on that, the robot can take a decision in which kind of container to pack it and to optimize the packaging. So what's playing now in the sequence is the automated tool changing sequence. In this case, the robot decided that this parallel jot gripper would be the most appropriate for the job to pick this item. Then you can see the camera array around the pile. And once the object is picked, just quickly skip, it's presented to instruments. This is what we're seeing now is an inactive demonstrator. So there is no active waste in this demonstration. So it's a simulation of the measurement, but this is what it would look like. And then it can be packed to the appropriate container. Here we have a similar sequence here. I won't play all of it, but just so you can see now, we're using the vacuum gripper to pick a piece of concrete. So a very, very similar sequence. just from a different point of view. So this is one example of the layout, but this is a very modular system. The vision system, the containers, everything could be reconfigured to fit a different use case. Here it's really demonstrating the software and the different elements working together. So just in conclusion, just key points. I think first we should take an automation mindset when we plan work on site. And I think we need to remember the 3Ds of robotics. If it's dirty, dull, or dangerous, we should leverage robotics. Then we've seen different applications and different ways of operating robots. It's not always about full automation. There's data collection, augmentation, and in some cases, automation with overlaps between these modes. And I just want to finish by saying that at SNC-Lavalin and Atkins, our approach to deliver robotics is to be the integrator and to work collaboratively with supply chain partners, OEMs, academia, and deliver the turnkey solution. So wherever you fit in this diagram, if you have an interest in robotics, please feel free to reach out. And here's my contact information. So thank you very much.
Thank you very much, Christian, for that. So we have a question on the chat. The first is about on-site welding. Is welding directly a pipe or so on-site? Do you consider this task as too much constraints, or what do you think?
Yeah, no, I think it's definitely possible. I've looked at one of these applications. It's definitely possible. In some cases, we've done laser cutting. Some of the similar constraints around fumes possibly and all the risk constraint with using a laser cutting tool, I think would be similar to welding. So of course, the application needs to be identified or looked at specifically, but in general, yes, welding would definitely be possible. That's something we're looking at.
Okay. And the other question is about the maintenance of the robots in their own environment. That is in integrating contamination, access, all this kind of stuff. What are you pushing?
Again, it will depend on the scenario, but definitely it's something that we need to be planned. If I look at the laser cutting modules, for example, in between each skip that is cut or each glove box that is cut, there needs to be an access plan to clean. Although some of the cleaning can actually be automated with the robot. We're using a vacuum cleaner with the robot to clean some of the cell, but there's still going to be some cleaning. So it has to be managed case by case. If we look at spot, for example, depending on the environment, when you send it, where you send it, you can cover the feet and remove protective covers. In some cases, you'll need a full suit and you'll need to clean other areas. So it's normally something we can manage and plan for.
Okay, another question. I'm left for that. What are the limits for the development of such high-tech technologies? And my question on that will be, so what is the next revolution you see for robotics?
Well, I think, I'm not sure we need to talk about revolution. I would think about using existing technology first. That's what I'm trying to accomplish first. There's other industries that use robots already. I would start by trying to leverage that and apply existing technology. But then the next step would be, I suppose, a higher level of collaboration between humans and robots. Especially if we look at use cases in nuclear industry, if our objective is not always to automate, if safety is the main objective, then teleoperation is a great technology. So I would look at things like avatars and haptics and telepresence technologies. I think this would be something definitely appropriate for the nuclear industry, where we're not always trying to replace humans. We're just trying to give them a way to work safely at a distance.
Okay. Maybe a last question before we move on to the next presentation. What are your considerations about radiation hardenings of robots and sensors? Because they operate in a harsh environment.
Yeah, definitely. So in the laser, it will depend on the environment, obviously, what kind of radiation is active in these environments. But currently, our industrial FANUC robots have been running for about a year with no signs of failure. So because we don't have that much data, what we're doing is we're measuring the level of radiation that these robots are being exposed to accumulate data on the performance and at what time will they start failing if they do. on Spot, the robot, for example, on mobile robots, there's been some tests done by Boston Dynamics where the robots have been exposed to 4 sieverts or 400 rems and have not failed, have not shown any sign of failure. So in some cases, radiation hardening is not necessary. So the approach is to try and use commercial off-the-shelf components as much as possible, measure the data to know what the real limitations are, and by exception, maybe we have to develop some radiation hardening, but that's not the default approach right now.
Okay, thank you very much for that. Now it's time to move to the last presentation for today. So, Sebastien, up to you.
Yes, thank you, Patrick. So, last but not least, I want to welcome Mrs. Véronique Remande and Mr. Pierre Noll from Egis company. So they will present us the use of extended digital twin solution for asset management for a specific application for bridges. So short bio, Véronique has been working for 20 years at Egis in the management of transversal projects. After she moved to as BIM manager on HPC in Clay Point project. And now she is part of the digital transition pool of the business unit devoted to large structure in Egis. And Pierre is developer mainly on JavaScript and Python. So please, the floor is yours.
Okay, fine. Thank you. Good afternoon to everybody. So the last presentation, we are going to give you a point of view about digital twin for asset management based on innovative BIM and GIS solution. So first of all, I just wanted to give you a quick presentation about Egis, just a few words. So Egis is an international leading global consulting, construction, and engineering and operating firm. We work side by side with our clients to build a more balanced, sustainable, and resilient world. Egis spans over 9 core systems integrating transport, energy, water, buildings, and city activities. And one of our specificity is that we also operate infrastructure, in particular roads, airports, and urban parkings. And we are a leading player in major nuclear projects globally, with a strong track record that goes actually back to 1948. We offer deep expertise across third and fourth generation reactors, fusion reactors, small modular reactors, and civil and military nuclear facilities. And as architects, engineers, we help our clients to manage complex projects across the full life cycle, greenfield, new build, install base, and decommissioning. And actually, so for the last 10 years, digital transformation is really ongoing through our project and inside the company. And when we are talking about digital transformation, we are talking about BIM modeling, BIM management processes, retro engineering, 4D planning, use virtual reality technology, mobile application, and work instrumentation with IoT and actually GIS solution, Geographic Information System. And for the 20 years, actually, we are working with GIS solution, especially S3 technology, and for environment study at the beginning. And GIS can be used as a cornerstone in project management for cartography analysis, decision-making tool, field working, and GIS is connectable and can be connected with other solutions. And so with Pierre Noll is going to present a digital twin maintenance solution that we we set based on BIM and GIS solution implemented on infrastructure project, bridge project actually. So in this sequence, we propose you a benchmark session because we are really convinced that this solution, GIS based on GIS technology, is applicable to nuclear activities for maintenance solution, including predictive and curative maintenance.
Well, what is GIS? So GIS stands for Geographic Information System. So it's a system which is a group of elements that interacts together according to a set of rules to form a unified whole. So in the geographic information system, the purpose is to have a system that can create, that can manage, that can analyze and display geographical data. And you know about 3D model. Well, 3D model may be a part of a GIS. And the purpose of this presentation is to show how here at Egis we use GIS systems as a central piece to visualize and cross data from various systems. And this will enable us to do some real-time reporting with collaborative tool. This will allow us to do decision-making on multi-criteria analysis. And in order to illustrate how we use GIS application, we'll use a sample project that we had and that derives from a maintenance contract to inspect approximately 60 pontoons and also to create structure inspection reports every 4 months. So in order to do that, we built a GIS system at the center of which we find a GIS viewer. So this is the central part. This is the main elements with these elements, all the actors of the project will interact with. This kind of the landing page of the system. And around this element, we find, well, the 3D model that will hold the geometry and the geographic informations about the different elements of the structures. We have an asset management system that will hold the information about, well, the asset management of each element. And in a broader approach, we could have IoTs that will feed real-time measurements and informations about the elements. Also, we have on the scope of this project field surveys that are used to gather information from the field. So you notice that we are not talking about nuclear facilities here. So this is a viaduct, and to give everyone a little bit of context on the elements of the viaduct, here is a small presentation. So we get mainly the beams. So here is the cross beams. Here is the main beams. On the top of the beams, we have slabs. Mainly for the substructure, we have piers and columns that are below the superstructure. And of course, we're gonna do some maintenance operations. So we have to go with a ranking. So here's the ranking we use with the colors. So we go from gray for not inspected to red for fail and a repair immediate. So moving on now to the the center element that we see later on our system. So we see that we have a landing page. So currently what we're presenting here is the central elements of the system, the GIS viewer, which is based on Egis online software. In this system, we get a first page where we can find some general information about the project, but also about how to use these elements, this tool, to get the information that we want, given who we are, because there are many people that can contribute to a project, and everyone have to have their own vision on their own usage of the GIS viewer. So this is about the main page, and we can embed some elements. So for instance, here is a 3D model that we have on the applications, and we in one site we can see that the main slab here is for a recommended repair because it is in yellow. So already in this view we have a cross analysis that takes the 3D models and the asset management system together. So this view is about crossing data from BIM modeling and also asset management or other external systems. But a more operational in the place of a maintenance operator would be a dashboard that we built to get only the data that we want in one site. So maybe with this view we want to get only the elements that should fall into the immediate repair category. So there is a system of filters up in the top bar, and so we can select and filter only the immediate repair. And we can see that we have 5 inspections that falls into this category, and here is the repartitions of these inspections. So we see that mainly we have 57% of the immediate repairs that falls into the expansion joints, and here 14% that is for the pier columns. Below there is the list of the different inspections, and in the middle we find the detail of a selected inspection. And on the map, on the 2D map here, we can see the locations of the forms. So we can see the red pins that shows where are the current inspections that are filtered. So when we click on one, you can see the detailed information about the survey. And now, for instance, we filter about -1 in gravity, so we pick an urgent repair, and we see that we get 27 of them, and that there are mainly on the here with the orange pins. But we also can get direct information about the survey, like the pictures along that goes with the inspection form. And here are some examples of the pictures that we get from the survey. So this gives an overview of what we can do with GIS solutions. And of course, this dashboard solutions make it possible to follow the diagnosis made in the field as soon as they are synchronized with the centralized database. So we talk here about the single source of truth, which is synchronized in real time with the field operators and with the maintenance operator that can see this dashboard. And also we can personalize this dashboard with many elements. And so this approach is really about the collaborative aspect, and with the applications on the field that fed the report, the dashboard, and tomorrow this dashboard can be also fed with IoTs or more real-time data. So, Véronique, do you want to say some final words?
Okay. Actually, yes. Like I said at the beginning, the tool that we give you some information was not made about nuclear project, but actually we made. We are quite convinced that this kind of solution can be really applied and can be helped to manage nuclear facilities actually. So I don't know if you have any question or if you want to launch the discussion about that. But,
thank you.
Thank you, Pierre and Véronique. We have a couple of questions. So the first question is, what are the standards used to make all GIS sub-elements sharing data?
Sorry, can you address?
Perhaps, Jean-Bernard, if you want to clarify your question, if you want to take the floor and open your micro.
For standards to make all GIS sub-elements sharing data. Actually, we use the IFC actually for the 3D models.
Yes.
The structuration of through the IFC, and otherwise for GIS, I don't know exactly.
I can't respond to that either for the GIS part.
Okay, so your answer, you use classical IFC standard for the
3D
standard
model, actually, yes.
Okay.
Mm-hmm.
Okay, and okay, Jean-Bernard asked another question. Any application-dependent standards? That's the question link, perhaps. Who is first?
I don't think
No,
so.
I don't understand the question.
Yeah.
Any application-dependent standard?
Okay, let's move to the second question. Okay, so the second question is the GIS able to send data to back office applications such as PLM or data are going directly upstream to the GIS viewer?
Data to back
Actually, the main part here was the GIS viewer. So this viewer is, the part that we present today is the part that are used by maintenance operator, and this gives a sight of what is on the field, and it can be used to make decisions with multi-criteria analysis and crossing informations, but it is not used to edit data through the GIS. It's more like this for decision making. So of course the GIS is able to send data back to other systems, but that depends on which systems. Actually the current asset system management that we had, it's not it's a brand made it's a custom made asset management system, but it can be replaced with another one.
Mm-hmm. And actually, the GIS system should be, from my point of view, will centralize main data, and the data can came from different systems such as PLM or asset management system or over database actually. But in order to run the GIS solution, a new database must be set actually, but links can be done between all the databases actually. Yes. But it's the GIS solution is a way to centralize and could be the single source of truth, like Pierre said. And it's a way to simplify the access of the data and to treat all the information and to set for the users through the dashboard that has been shown you just before. And it's in order to set a real decision maker tool actually.
Okay, thank you. I think we have no more questions, so we can perhaps close the session. I will thank everyone for attending this session, with special thanks to our today's speakers. Do not hesitate to attend the coming next Index virtual session on the 12th January. It's next Monday, with the same panel session on digital innovation for nuclear safety application. And also we've got a keynote on regulation of digital industries. Patrick, you want to add something?
No, we have to remind that there is a tech demo at 4 p.m. today, same channel, so we have to mention that. And the same as you, I thank you for all speakers and for attending this meeting. We were in between 100 and 120 people attending all the presentations. So thank you everyone, and have a nice day. Bye.
Thanks a lot. Goodbye.
Bye.